So in this section we're going to cover a lot of messy code. There's been a lot of code, but quite a lot of it is quite messy, but it does kind of introduces a nice layer of abstraction and you know, more readable code in a way. So not at this stage it wouldn't look very readable, but later on figuring out mistakes might be easier with this sort of code that we've written. So let's take a look. But before I get into the messy side of the code, we'll just look at some of the abstraction we did before that. So, I mean, if you look at the application.cpp file at the moment, it will be very cryptic because we've added quite a few stuff here. But we have essentially abstracted away the index buffer layout and the vertex buffer layout. So before going into the code we've added later, which is all this stuff here, which is something we'll talk about after we've talked about the buffer layouts. So, in fact, this buffer layout class is something we'll talk about later as well. So let's take a look at not another layout, but the buffer itself. So we've got vertex buffer and we've got index buffer. So since this is buffer.h, it must be pretty clear at this point that this is an abstraction layer. Yeah. So we've got these virtual functions, we've got virtual destructor, bind and bind, again, layout stuff we'll talk about in a minute, vertex buffer, and we've got a create function, which allows us to create different implementations of, depending on the graphics API we're using, so that's something we'll take a look in just a minute. So these two are static functions, and they basically are the reason why we need a buffer.cpp. So if you look at buffer.cpp, we have we're including a renderer file, which if you take a look at that, at the moment the render file, all it contains is an enum class called render API, and at the moment, because we're not thinking about DirectX or anything, we just got none and OpenGL, and the class, so that's just a enum class, and this is a class renderer. And what we do inside the renderer is we create this inline static function, render API, get API, so it returns render API and as a get API function, and basically it returns the one we've selected. Okay, so one of these, which is and the render API is basically a static private variable for this class. So when we inherit it, when we include this render.h in our buffer.cpp, what we do with it is we do a switch of the API that's returned by the renderer. So you're probably wondering where do we actually assign something to the render API variable inside renderer. So that's actually in renderer.cpp, and all we're doing in renderer.cpp is basically we are assigning that private variable with OpenGL type, which is something that's a type of render API. So that's all we're doing at the moment in renderer.cpp. So if we come back to buffer.cpp, we're switching that whatever is returned by the get API, and if it's none, then we just say we don't support that at the moment, and we just assert that. And if it's OpenGL, then we just return a new OpenGL vertex buffer with the vertices and the size. And same thing here in index buffer, we do the same sort of stuff. We assert if it's none, and then return an OpenGL index buffer. So let's take a look at those. So if we've got OpenGL buffer.h. So this is where we create our vertex buffer and an index buffer specific to OpenGL, and we've got the constructor that takes in the vertices and the size that's returned that's provided by the by the create function, which basically returns this an object of this type. And we've got the virtual destructor, bind and bind, buffer layout is and so layout is something we'll talk about in a minute. We've got the mrender ID, and again layout stuff. Same here in index buffer. So let's take a look at the CVP file. So, oops, that's the wrong CVP file. Let me close that. Buffer.cpp. Okay. So as you can see, we've got the vertex buffer and the index buffer, and in the constructor we are just doing the GL create buffer, GL bind buffer, and GL buffer data. obviously, even though we were using create buffer, apparently it doesn't just get rid of this extra line as we thought initially it would. So we still need to bind the buffer, and then we do the buffer data and all that stuff. So this is where we put all our OpenGL specific code that we were using in the application.cpp file before. So this is pretty straightforward. So let's get to the a bit messy side of the code. But before that, I've actually gone ahead and provided an abstraction for the shader as well. And if you look at shader.h now, that's pretty much the same. But I've just provided this extra create shader function, which is static. So same sort of structure as we saw in the abstraction of the buffer. The two buffers. So if you look at shader.cpp, I'm doing the same sort of get API and switching between the none and OpenGL and doing the same sort of stuff, and I return a new OpenGL shader with vertex source and fragment source passed into it. So if you take a look at that, so shader, OpenGL shader.cpp. In fact, let's just look at this H as well. So yeah, as you would expect, everything's the way it was. We just created a constructor here where we pass in the vertex and the fragment source. And in OpenGL shader CPP, what we're doing is shader specific code again. We've gone through this already in an earlier video, so I'm not going to go through it again. But we've just abstracted it away, same as we did the buffers. So let's talk about the messy code now. So the messy code is well, in buffer.h, basically this is where we add. So it's not complicated, because all we're doing, if I go into application.cpp, I'll just use that application.cpp. So all we're doing is providing a way to automate this, what the stuff we pass into the GL vertex attribute pointer, and obviously here it's just we're enabling the attribute array, but we're just automating this part. Okay, so this is where we provide the layout of our vertex, vertex. So how do we automate that? So that's all we're doing, but it's a bit complicated because we provide our own data types and all that stuff. So let's go through all of that. So first of all, we've got enum class shader data type, which basically has the common types you would be likely to be using if you're doing some shader programming. And we've got float, float2, float3, float4, mat3, mat4, bool, int goes up to 4. And in here we've got a static function that returns a uint shader data type size. So we just go through all of those types and we just return their size. So just single float would be 4, and then two floats would be 4 times 2. And matrix, we've got, if it's a 3 by 3 matrix, it's all going to be, we're just assuming that even in the matrix we're going to have float values, so we just multiply the matrices by 4 as well. And in integer we've just got, integer is 4 as well, size 4, so we just multiply that by 2 and 3 and 4. Okay, so that's how that works. And down here we've got a structure called buffer element, and what that contains is the name, the shader type, the shader data type, so this thing here, and it's got size, offset, so all the things that you would expect to put inside a vertex attrib array pointer thing. I hope I said that right. And here we're providing a constructor, a default constructor, because otherwise it's going to complain if you don't create a buffer element object without providing all these extra parameters. So we always provide a default constructor, just in case we just need to declare this type and not assign it immediately. So that's why the default where default constructor comes in. And then we basically more of where we actually provide these parameters, so shader data type, the name, and whether it's normalized or not. Clearly that's not a compulsory parameter, so it's going to stay false if you don't provide anything. And then it basically initializes those with the values passed in, and for some of them it just calculates it or just sets it to 0 in case of offset. Okay, so So here we're just getting the component count, so in case it's float, we're just gonna have 1. So yeah, depending on how many elements a particular component of the vertex has, we're gonna return. Like if it's like with position, we'll probably use float 3, which is gonna be x, y, and z. So that's gonna return 3. And if we add extra information to the vertex, so if we add color, then we probably would be using float 4. So that sort of stuff is happening here. That's gonna return 4, obviously the count. We could obviously calculate the count on the fly, but we're not doing that. We're just doing it this way. And then we have the BufferLayout class. So again, we've got a default constructor, and then we've got a constructor that takes in an initializer list of buffer element type as a reference, and then initializes m_elements, which is a private variable of this type. Actually, it's a vector of this type, so it initializes whatever is passed in here with this. And then we are also calculating the offset and stride inside the constructor itself. So this function, you can look down here in the private. What it's doing is it's taking setting the offset to 0, stride to 0, and then it just goes through every element in m_elements, and basically it sets offset to whatever it was for. So down here is adding offset as the size of the element to the offset. So next time it goes through this loop, it just sets element offset to this offset that it calculated before here. So for example, if you've got position, which is 3 elements, so it's going to get well, offset is basically in bytes, so it goes through the 3 elements of float type, so that's 12 bytes, and then it just assigns 12 here. So first time it goes through here, it's going to be 0 obviously, and then it's 12 here. So when it gets to, say, like, the color part of the vertex, it's going to set offset to 12. So that's where the pointer starts from if it's actually looking for the colors. So that's what the offset actually lets the shader do. And obviously we're adding to the mstride. Mstride is basically just collecting the whole size of a vertex. So if it's got 3 elements, 3 floats for the position, 4 floats for the color, then in total it's gonna have 12 plus 16, which is 28. Yeah, I think it's 28. Anyway, so that's going to be the stride, obviously. So that's the whole thing in total. And yeah, so, and obviously down here, because it's related to the vertex, providing a layout for the vertex, we provide these functionalities inside the vertex itself. So we're providing a const BufferLayout, const get layout function that returns a BufferLayout as a reference, and that's pure virtual. And we've got set layout, which is also a pure virtual, and sets it as a const reference. And if you take a look at the buffer.cpp, so buffer.cpp actually so if you take a look at OpenGL buffer.h, which is where the OpenGL implementation is, we can see these virtual pure virtual functions have been provided an inline definition. So it just returns mLayout, which is a private member here, and set layout basically sets the layout, which is passed as a reference, with the value of mLayout is set as the layout, which is passed as a reference. But as you can see, none of that layout stuff has actually leaked into the CPP file, so CPP file is still as it was. It's just we've provided 2 inline functions inside the header file, and that's mostly it for the buffer.h and the OpenGL side implementation. So let's actually take a look at the mess we have made in application.cpp. So this is a mess, which clearly does not belong here and probably will need to be removed to some other place. If it needs to exist in the first place, I guess it probably does. So all this is doing is shader data type to OpenGL base type, takes in the shader data type, and just, if it's float, then it returns GL float. If it's integer, then it returns GL int, and if it's bool, it's GL bool. So that's all it's doing. But it looks, it doesn't look messy, to be honest. It's pretty it's pretty structured, but it clearly does not belong in application.cpp, and that's why it's a bit messy. We come down here, vertices. So as you can see, we've just added 4 more floats to the vertices because we're also providing color, just to show you that this functionality works. We don't need to, I guess, but we're doing that. So and here we've just created this extra scope just to see that, just to show that this layout variable does not actually leak out here to this one, which is, we could have just named it differently, but we're just demonstrating right now, not really doing the final implementation. So what this buffer layout type layout does is because the constructor, as you remember, for buffer layout, if you take a look here, buffer layout, the constructor takes in and initializes a list of buffer elements as reference. So this is what the initializer list looks like. It's just curly braces, and you pass in the values inside there. And as you can see, we're not passing in the normalized value, so it remains as false. And so it passes in those. So those are 2 elements. So those are 2 buffer elements, as you can see here. So the buffer element type. So we've provided 2 buffer elements, and that's gonna then become a vector of buffer elements. As you can see, it just gets elements gets initialized with these elements. So we take it in as initializer list, but we then just pass it into vector. So what we do next is just set layout with this layout. So remember, we pass layout as a reference. So inside the mvertex buffer, we have that private variable buffer layout, and we just set that equal to this layout, and because it's passed as a reference, it's actually just pointing to this same variable here, or well, it kind of gets destroyed, so it's not really pointing to it. No, it's a new variable. So down here we've got a const auto reference where we're just getting the layout that we just created in here. Just provided the layout to the mvertex buffer, and then we just retrieving it from the vertex buffer here, and then we go through every single element inside the layout. So at the moment we just got 2 elements, so 2 elements, a position and a color, and we go through those. And so when we're at position, the index is going to be 0, and when we're at color, the index is going to be 1. Then we just provide all those things that we automated here, so we don't need to worry about what we provide in here, because it's all automated at this point. So we just do element.getComponentCount, which provides how many components are in one buffer element. So for a position it's 3, for a color it's 4. We do shader data type to OpenGL base type element.type, so that just returns us the OpenGL type, as you can see up here. And for normalized, we just check if element.normalized is true, then we just return GL true, otherwise we return GL false. And because it's false, we're going to return false. And layout.getStride gets the stride, and we then just do element.offset, which is going to be 0 and 12 respectively for position and color. And because it has to be casted to a pointer, we just cast it to const void pointer, and we just increment the index, and that's all we're doing. And down here, just to show you that the functionality works, we're taking in the color, which is at location 1, remember, because the index is going to be 1 when we get to the color buffer element. So we then send that out as a varying, so we take in as an attribute up here from location 1, and then we just send that out as a varying, and we set vColor to a color, and once it gets sent to the fragment shader, we take it in here, and we just then override whatever was passed in here with color equals vcolor, and that should give us something like anytime now. Am I even running it? Yes, I am running it. It's just being slow. Okay, so let's pause that. So this is what we get, basically. Right. So we go here. So why do we get that color? Well, because we've got pink, blue, and yellow, and these three different vertices. So it's just interpolating between those colors, and that's why we get this. So that's all there is to it.